In this section, we talk about the multiplicative group of a finite field. Let P be a prime number, and let F be a positive integer, and let Q equal to P to the F. The main theorem of this section states that the multiplicative group of a finite field is always cyclic. Of order Q minus 1. Here FQ is a finite field with Q equal to P to the F elements. And the multiplicative group is a subgroup formed by all non-zero elements of F sub Q. So there are Q minus 1 elements here. And the theorem says that this group must be cyclic of order Q minus 1. To prove the theorem, we need two lemmas. The first lemma is a lemma from elementary number theory. If n is a positive integer, then n is equal to sum phi of d for d taken over all divisors of n, where this phi is the famous Euler phi function. Phi of d is equal to the number of integers between 1 and d that are co-prime to d. And now let's prove this lemma. Here we will present two proofs. The first one is elementary, and the second one involves basic abstract algebra. So this is the first proof. Let us consider the following decomposition of the set of integers from 1 through n. We decompose this as a disjoint union A of d for all divisors d of n, where each set AD is a set of integers k from 1 through n such that k and n has GCD equal to d. This means the GCD of k and n is equal to d. GCD means the greatest common divisor. And now if you divide both sides of this by d, this is the same as the set of all integers k from 1 through n, such as k divided by d and n divided by d are co-prime. This is a basic elementary number theory. And now we make a small change of variable here. I claim that this set has a 1-1 correspondence. 1-1 correspondence with the set of integer L's from 1 through n divided by d, such that L is co-prime to n divided by d. Explicitly, this 1-1 correspondence is done through k divided by d corresponding to L. So element here corresponds to element here by division by d. And because this is a 1-1 correspondence, those two sets must have the same cardinality. So if we call this set B of d, so this is A of d, this is B of d, then if we take the cardinality of both sides, we see that n is equal to the sum of the cardinalities of A of d's for d as divisor of n. And this is same as the sum over all divisors of n of the cardinality of B of d. And now, what is the cardinality of B of D? Look at the definition here. You realize immediately the cardinality of B of D is precisely phi of n divided by d. This is just by definition. And this last term is equal to, if you do a change of variable by replacing n divided by d just by d, we see that n divided by d is a divisor of n, is the equivalent to saying that d is a divisor by n. So by a change of variable, we see that the sum is precisely the sum of phi of d's for d divides n. And this proves the lemma. Now let us talk about the second proof, which is based on abstract algebra. If d divides n, let C sub d be the unique subgroup of Z mod nz of order d. Explicitly, CD has the form it is a subgroup of Z mod nz generated by n divided by d. Let me explain a little why this is unique. Indeed, if CD prime is another subgroup of order d of Z mod nz, and from abstract algebra you know any subgroup of a cyclic subgroup must also be cyclic. And we may assume CD prime is generated by L. Here little l is between 1 and n minus 1. Now because CD prime is also of order d, the order of its generator must be equal to d. So the order of L bar must be d. What does this mean? This means n must divide d times L. Namely, the d multiple of L must be divisible by n. Or equivalently, n divided by d must divide L. Therefore, this L must be a multiple of n divided by d. So L must live in CD as well. So L bar must also be in CD. Because the generator is in CD, it follows that CD prime must be contained in CD. But you know CD prime and CD have the same cardinality. Therefore, those two subgroups must be equal. And this verifies the uniqueness. And now let's go back to the main proof. Let capital phi sub d be the set of generators of C sub d. Then we know the cardinality of phi sub d must be equal to the little phi of d, where this little phi is a Euler phi function. This is because any cyclic subgroup of order d is isomorphic to Z mod dz. And we can always represent Z mod dz by 0 bar, 1 bar through d minus 1 bar. And from here, it's clear that the number of generators in this cyclic subgroup of order d must be precisely phi of d, namely the number of elements whose represented integer is coprime to d. This is a very basic fact from abstract algebra. This explains this identity. And now we make a claim. We claim that Z mod nz can be written as a disjoint union of phi sub d. And now let us check this claim. To check this claim, we first show that any two members here are disjoint. Indeed, if d and d prime both divide n, and d not equal to d prime, then we must have phi sub d intersection with phi sub d prime equal to empty. Why is this so? This is because any element from phi sub d and any element from phi sub d prime have different orders. Because they are both generators, with X being a generator of a cyclic subgroup of order D, and X prime being a generator of a cyclic subgroup of order D prime, and D prime are not equal. So the order of X, which is D, and the order of X prime, which is D prime, are also not equal. Therefore, X and X prime cannot be the same element. But they are arbitrary, so this means the intersection of these two sets must be empty. So this verifies the disjointness of the members on the right-hand side. On the other hand, for any element X in Z mod Nz, by group theory, the order of X must divide N, and X must be in the cyclic subgroup of the order of X. Remember, at the beginning, I explained to you that this is a unique subgroup of order D. Therefore, the subgroup generated by X, which is the subgroup of the order of X, must be identical to C sub the order of X. So in particular, X must be in C sub X. This is because C sub the order of X is a unique subgroup of the order of X. And this element must also be the generator of this, which means X lives in phi sub the order of X. Therefore, this shows any element in here must live in one of these. And this verifies the claim. Now, we can conclude the proof. N is the cardinality of Z mod Nz. And by this disjoint union, this partition, we know this cardinality must be equal to the sum of the cardinalities of phi sub d's for D divides N. But we have already seen that the cardinality of each phi sub D is equal to little phi of D. So the right-hand side is equal to the sum of phi of D's for D ranges over the divisors of N. And this is exactly what we need to prove in this lemma. Now we introduce our second lemma. Remember that our main theorem of this section says that the multiplicative subgroup FQ star of the finite field FQ is cyclic of order Q minus 1. To prove this theorem, we need to understand when a finite subgroup becomes cyclic. And our lemma 2 provides a way for us to tell when a finite subgroup becomes cyclic. Let H be a finite subgroup of order n. Suppose that for all divisors d of n, the set of elements in H such that the dth power is equal to 1 has at most d elements. Then we can conclude that H is cyclic. Now let's prove this. Let D be a divisor of n. If there exists an element x from H of order D, then the subgroup generated by x, consisting of elements 1x, x squared all the way to x to the d minus 1, is cyclic of order D. And now we make a claim. We claim that all elements y in H with y to the d equal to 1 belongs to this subgroup generated by x. Why is that so? This follows from our hypothesis. First of all, we know that the subgroup generated by x must be contained in the set of y's whose dth power is equal to 1. This is clear because x has order d, so x to d is equal to 1. And so is every element in the subgroup generated by x, 1x all the way to x to the d minus 1. But by our hypothesis, we know that this set has cardinality less than or equal to d. So this part follows from this hypothesis. But on the other hand, we know because x is of order d, the cyclic subgroup generated by x has cardinality precisely equal to d. This is equal to d. And this cardinality is less than or equal to this. So, by squeezing, we must have the cardinality of this guy is equal to the cardinality of this. So as two sets, they must be actually equal. And this verifies this claim. And now, an immediate consequence of this claim is that all elements in H of order D must satisfy this equation and therefore must belong to the cyclic subgroup generated by X. And because those elements are of order D and X is also of order D, those elements must also be generators. But how many such generators are there? By elementary group theory and number theory, we know that the number of generators of the cyclic subgroup of order D is phi of D, where phi is the Euler phi function. Now we make a second claim. We claim that the number of elements of order D in the group H is either 0 or phi of D. For any D, a divisor of N. This immediately follows from our discussion above. Because for any D, a divisor of N, first there be no elements of order D at all. In that case, the number of elements of order D is 0. Now, suppose there exists at least one element of order D for D divides n. Then by our discussion above, as a consequence of this claim, the number of all such elements must be equal to phi of D. So this claim immediately follows from our discussion. Now let us summarize what we have here. First, H is a finite subgroup of order n. Order of H is n. And by our lemma 1, n is the sum of phi of d's for all divisors d of n. This is our lemma 1. But on the other hand, if you look at the left-hand side, because H is a disjoint union for D divisor of n of elements in H of order D. So the cardinality of H is equal to the sum for D as divisor of n of the cardinality of these sets. But from the second claim down here, we know that the set must have a cardinality of either 0 or phi of D. So this guy is either 0 or phi of D. And as a consequence, if we compare this guy with this guy and look at each summand, because this is always bigger or equal to this, but as a whole sum, they are actually equal. What does this mean? This means each summand here must be equal to each summand here, which means for each summand here, it is impossible that the cardinality is 0. This is the only case. So let's summarize. This forces the number of elements in H of order D is equal to phi of D for all D divides n. And in particular, if we put D equal to n, then this says the elements in H of order n is equal to phi of n, which is at least 1. So there exists an element in H of order n. But H has cardinality precisely equal to n, and this element is of order n. What does that mean? That means the H must be generated by this element. And this proves that H is cyclic of order n. Which is what we want from this lemma. And now we'll use our lemma 2 to prove our theorem 2. To use our lemma 2, we let H from lemma 2 be the multiplicative subgroup FQ star of the finite field FQ. And we take n equal to q minus 1. N is the cardinality of this guy. Because this is, as a set, just fq minus 0. And we claim the equation x to d equal to 1 has at most d solutions in fq for d divides q. And thus has at most d solutions in fq star as well. And because 0 is not a solution, 0 to the d is 0, not equal to 1. So this equation must also have at most d solutions in fq star as well. Why is it so? Indeed, this is because fq is a field. So the polynomial ring fqx is a unique factorization domain, UFD, unique factorization domain. And from basic abstract algebra, you know that in a UFD, this polynomial of degree d has at most d solutions, d roots. And because 0 is not a root, so it also must have at most d roots in fq star. And this verifies the claim. Now, by our lemma 2, we know that H, which is now fq star, must be cyclic of order q minus 1. Finally, I would like to make a remark here. Actually, our proof above shows something more general. That all finite subgroups of the multiplicative group of a field are cyclic. And this field does not even have to be finite. This is because if you go through our proof, here we only use that the fq is a field to conclude that x to d has at most d solutions in this field. This claim is still true if fq is an infinite field. As long as our group H is finite, then this argument still runs through. And we still get, for any little x in H, that x to d is equal to 1 has at most d solutions in H. So this lemma still applies. And therefore, all finite subgroups of the multiplicative group of a field are cyclic.